So hello, this is now the lecture for week 3, day 1. So what will be covered in this lecture will be mainly the extension now from purely one-dimensional motion in the horizontal direction and purely one-dimensional motion in the vertical direction, now combining these two motions into 2 dimensions. I will first begin with a recorded review of an in-class problem, what we did in class, the car and motorcycle problem as a reviewer of horizontal one-dimensional motion, how you approach this, how you combine two independent motions, namely the motorcycle and the car together. I will then review vertical motion, so now we're going from the horizontal to the vertical direction, and then review and extend and finish this problem what I started in class the last time on Thursday, namely the vertical throw. There are these three cases for that. That was quite extensive. And then comes an introduction into two-dimensional motion. And there will be the first in-class problem today, namely the horizontal throw, where you have two overlapping motions, namely in the horizontal direction and then in the vertical direction. So that covers the bulk of the class for today, week 3, day 1 on Tuesday. And I strongly encourage you can pause and play this video. It combines slides, it combines handwritten notes on my iPad. You can pause and play. Take advantage of this. Don't just listen to that and watch this like a regular YouTube video, but take your own notes and think about it. Go back to that. That's the main essence of an educational video like that. Thank you. Okay, so let's begin with week 3, day 1, mainly on a discussion of two-dimensional motion, which is the main focus for chapter 3 in your textbook. So let me first provide you with an outline. I want to first go back, in fact, to one-dimensional motion to review this topic very briefly, and then, in fact, review as requested to calculate this in-class problem, the car and the motorcycle again, and record this, in fact. I will then review we are leaving then one-dimensional motion in horizontal direction, going then to one-dimensional motion in the vertical direction. We'll review that, and then we'll complete this extensive problem on the vertical throw, which I started in class last week on Thursday, week 2, day 2. And then we begin to combine both motions in the one dimension, both in X and Y, and have a general discussion about two-dimensional motion. In the first application of this will be an in-class problem of horizontal throw, where you throw a stone not just up in the air vertically, but you throw that stone. Let's say you stand at the edge of a cliff and you throw a stone horizontally down a cliff with an initial horizontal velocity, and then this stone is subject to a downward acceleration. It's a very classic problem. Okay, so let me first review basic aspects about one-dimensional motion, a constant acceleration model. What we considered here is now a model in which the acceleration is a constant, including the special case that a equals to 0, and these types of motion will be mostly considered. In the first case, where the acceleration is a constant but different from 0, we do have the following very basic relations. So a of t is a constant different from 0, then the velocity, and I derived this a while ago, is purely a function of time, but linear in time with the integration offset v0, meaning the velocity at t equals to 0 equals to v0. And this is what you always have to ask yourself: what are the initial conditions? So initial conditions concerning velocity at t equals to 0 is v0. Then integrating v of t further to come to the location x of t, you have then x0, v0 t plus a half at squared, quadratic in time for constant acceleration. And here comes the second important initial condition. What do you know about the initial location at t equals to 0? And often this is tied into choosing a coordinate system appropriately. Then the second case where now the acceleration is equals to 0. So what do we have now? Well, if the acceleration is equals to 0, then you can find out the answer directly from here. Then the velocity is simply a constant, meaning acceleration quantifies the rate of change of velocity. If that rate of change is 0, then the velocity is a constant. And then integrating this further, meaning a constant, then you have a dependency which is linear in time, meaning x naught plus v naught times t. So in summary, v of t varies linear with time for an acceleration equals to a constant, and x of t varies quadratic in time. Concerning now the case of a equals to 0, v of t is a constant, does not vary in time, and v of t, x of t varies linear with time. I hope this is really clear at this point. So let's now go back to this problem, what we talked about, namely a car is driving at a constant but unknown velocity v naught on a highway. A motorcycle is a distance d behind the car. Initially, they are both traveling at the same velocity. So imagine you would continue like this. They would just continue driving like this forever, maintaining that constant distance. But something is happening now. That minute where you observe that, the motorcycle starts to pass the car by speeding up at a constant acceleration am. So you observe the car is a distance d ahead of the motorcycle, and the motorcycle has the same velocity as the car but unknown, and starts to accelerate then with the aim to meet the car. When the motorcycle is side by side with the car, and this is now an additional constraint of this problem, the motorcycle stops accelerating and is traveling twice the velocity of the car. So, and there are now three parts to that. How long does the motorcycle accelerate? What was the initial velocity of the car and motorcycle? How far did the motorcycle travel while accelerating? Express all your answers in terms of given quantities in the problem, okay? So given quantity is the distance d and the acceleration am, but an unknown quantity is v naught here. Okay, so let's begin now the in-class problem on the car and the motorcycle, which I was just reading to you before on the slides. And as I said before, I strongly encourage you not just to simply watch this passively, but to pause and play and take your own notes with that. So the first thing I want to do is, when we're now dealing with this motorcycle car problem, draw two diagrams, namely a location versus time diagram. This is the first step when you're dealing with problems like this. In particular, when you want to relate the motion of two objects relative to each other and who have a given constraint. Like in this case, they're meeting at one point, and when they meet, a motorcycle has twice the initial velocity. All right, so here we have now x of t, and here on the bottom we come to that, we have now v of t. So let's first think about that. At t equals to 0, the motorcycle is a distance d ahead. So I decide now that I place the car is a distance d ahead. I decide now that I put the motorcycle at the coordinate origin. So the motorcycle begins here. The car is now a distance d ahead here. So this is literally that coordinate distance from 0 here is the distance d. Then it says that the motorcycle has no acceleration. So it undoubtedly has a certain initial velocity which characterizes the slope at t equals to 0. So that would be here. But then it has no acceleration, and therefore the car continues like this, namely functionally a straight line towards larger values than 0. Now, in contrast, the motorcycle has also an initial velocity, but it does have an acceleration. So at t equals to 0, when you draw now a parabola, since you have an acceleration different from 0, you do have an initial slope here, not t equals to 0. Remember when we were drawing this in class here. So you sketch this like this here, and you draw here two parallel lines, because the initial velocity of the motorcycle is exactly the same as in the car. And then you draw relative to that straight line now, you're sketching here a parabola. And then it said that this slope here when they meet is twice the initial slope here. So that slope characterizes the velocity locally here when they meet. So let me denote this time here as time tf, and location when they meet, I denote this here, and please use your own symbols to characterize this as location xf. So therefore we have now the functional form of x motorcycle of t, and we have here x car of t. And here when they meet here, that slope here is twice as large here, so the velocity of the motorcycle when they meet at tf equals to 2 v naught. Okay, so that is the situation for the x versus time diagram. Now let's talk about the velocity versus time diagram. So what we now have here is, let's first talk about the car. The car has zero acceleration, has a constant velocity v naught, and that continues like this. So this would be here v naught. And then the motorcycle also starts out with the same velocity at t equals to 0, but then when they meet, so this is roughly here, it has twice the velocity. So this is 1, 2, 3 in these units, 1, 2, 3. So this would be then roughly here. Okay, so the velocity increases because the motorcycle accelerates, and then by the time they meet, the motorcycle has twice the velocity here. So this would be here 2 v naught. So this is a complete set now of location versus time and velocity versus time graphs. All right. So now let's analyze this a little bit more quantitatively. What do we know about all of this? So we're talking about a constant acceleration model. So a equals to a constant here. Then therefore the velocity varies linear in time. V of t equals to v naught plus a times t, and location x of t equals to x naught plus v naught t plus a half at squared. So therefore now let's formulate the initial conditions first. So what do we know about this? At t equals to 0. So let's first do this for the car. So the acceleration of the car t equals to 0 is 0 and remains to be like that. The velocity of the car at t equals to 0 is a constant, is v naught, and the location of the car at t equals to 0 is distance d. It's a distance d ahead, and I analyze this in that coordinate system. So here we have the initial conditions for the car. Then we come now to the motorcycle. So for the motorcycle, what do I have? I have now the acceleration of the motorcycle at t equals to 0. I call this a constant am, and it continues like that. The velocity of the motorcycle at t equals to 0 is a constant, it's v naught, at t equals to 0. And the location of the motorcycle, which I put here by choice as the 0 location in the coordinate system, what you see here, equals to 0. So therefore here I have the initial conditions of the motorcycle now. So now there's an additional condition now to be fulfilled, namely besides the conditions at t equals to 0, namely at t equals to tf. There are two additional conditions that need to be fulfilled. Number one, the velocity of the motorcycle at tf equals to 2v0, namely twice the initial velocity. And when they meet, the location of the motorcycle and the location of the graph relative to here, to where they began from, relative in that coordinate system, they come together here. So therefore these graphs, these functional functions have to be identical at that time df. xm of tf equals to xc of tf. So therefore, let's now begin formulating explicit functions for the car and then the motorcycle. So for the car, we know the acceleration is 0, the velocity is v0, the initial velocity continues like that, and the initial location is d. So therefore, for the car, we can write down x car of t, and you literally insert these initial conditions into our constant acceleration model. So you replace x0 by d, v0, we use the same symbol v0, and a is 0. So therefore we have something rather simple. It's a function linear in d in time is v0 d plus v0 times t. And the velocity of the car is simply v0. Now let's come now to the motorcycle. xm of the motorcycle is now so x0, again we go back to our constant acceleration model, x0 plus v0 t plus a half a t squared, but now the initial location is 0 by choice, initial velocity is v0, and the acceleration is am. So therefore we have v0 t plus a half a t squared, and the velocity of the motorcycle equals to v0 plus am times t. So now all physics part is literally done. The rest is now algebra work, because we already formulated two conditions that need to be fulfilled, and now we have to evaluate the consequences for that. Namely, we need to evaluate what is the time and what's the initial velocity. But luckily we have two equations with these two unknowns, and subsequently we evaluate the total distance traveled. All right, so let me label these. This is page 1 here. So let's now formulate quantitatively these conditions here. So at meeting point, at the meeting point we have xm of tf equals to xc of tf, and we have the velocity of the motorcycle at time tf equals to 2v0. So let's evaluate simply the consequence, and we have explicit functions for x motorcycle and x car. So for the motorcycle, this was now v0 tf plus a half am tf squared equals to d for the car plus v0 tf. And then for the velocity, we have here v0 plus am tf concerning the velocity of the motorcycle at time tf, and that has to be equals to 2v0. So now this simplifies quite a bit. So let me first circle here the unknowns v0, and time tf. One equation but two unknowns, and luckily we have here a second one, v0, tf, and v0. So now this term here, v0, tf on the right hand side, v0, tf on the left hand side cancel out. And that's purely by choice, because I said the initial velocity of the motorcycle and the car is the same. So these terms cancel out, and then we have something rather simple. We have then a half am tf squared equals to d,
and we can solve this then for the time tf. So tf is therefore 2d. So you multiply this 2d and divide by the known acceleration, so divided by am, and then the square root of that. And then for the velocity we now have, so v minus v naught on the left side minus v naught on the right side gives you then v naught equals to amtf. So then we have here v naught equals to amtf, and therefore we have v naught equals to am times, and then we have here 2d divided by am and the square root of that, and am divided by the square root of am is the square root of am, so therefore we have v naught equals to the square root of 2 am. So this is now the final result for the time. And the velocity. So now there's one more thing I want to do here right now, namely the total distance traveled. Total distance traveled. That would be now xm of tf equals to v naught tf plus a half am tf squared. And so let's replace now. We have now a square root of 2 amd for v naught times, we have here 2d over am and the square root of that for tf plus a half am times, and this is here 2d over am. 2d over am squared, and then squared is 2d over am. So now this simplifies quite a bit. Am against am, 2 against 2. Then you have here 1 square root of am divided by square root of am goes out, and then you have here 2d square root times 2d squared is therefore 2d. And then you have here plus d, so it's equals to 3d. So the net result is therefore xm of tf equals to 3d. All right, so let's stop here. Okay, so now that we have solved this problem, let's now continue. Namely, let me first review now a vertical motion. So we are stepping away now from the horizontal direction entirely into the vertical direction here. And let's consider now here, and I derived this in class to give you a motivation why every object restricted to the Earth's surface, we're not talking about flying away from the Earth's surface to 10 kilometers above the Earth's surface, we're restricting ourselves to the Earth's surface. And approximately there, every object experiences the same acceleration, namely g, roughly 9.81 meters per second square. There's a slight variation from depending on the location. You probably remember that term g equals to the universal gravitational constant capital G times the mass of the Earth divided by the radius of the Earth squared. The Earth is not a perfect sphere, so there are some local variations to that, and some local variations around this value of 9.81 meters per second square. So this is only an average value. So what I want you to take away from this discussion is at any given point, objects in free fall have the same acceleration regardless of mass. And the other notion, what I want you to be aware of for the moment, I completely ignore the impact of air resistance. Now, near the Earth's surface, the value of this acceleration is essentially a constant, and we're taking this value to be g 9.81 meters per second square. And only when you're dealing with a numerical calculation are you supposed to use 9.81 or 9.8, and sometimes even, I will tell you, just for simplicity, use 10 meters per second squared. So now, since we're now dealing with constant acceleration, how velocity varies as a function of time and how location varies as a function of time is completely defined. Go back to the notes from last week on Thursday, where I defined a coordinate system with an upward y coordinate system, and associated to that a unit vector j pointing upward. Therefore, the velocity is v of t in the y direction, v naught plus ay times t. But ay is now the coefficient to a vectorial quantity characterizing the acceleration, but that acceleration is downward in the opposite direction to the unit vector j. So therefore we have here minus g. G is always a positive number, 9.81 meters per second squared. And therefore the location y of t equals to v naught plus v0t minus a half gt square. And often I would put here a little index here for y, in here for a little index for y, just to make sure clear, in contrast to the horizontal direction that we're talking about now, the vertical direction. Here's a very beautiful photograph. This strobe photo of a falling ball shows increasing spacing resulting from the acceleration of gravity. Strobe photo meaning you take snapshots in equal time, but when you do that, location does not vary equally as much, namely proportional to time, as you know, but quadratic in time. And therefore these distances y here is increasing as you move along in time. It is directly a reflection of this quadratic dependency in time. So now, how does now the location versus time graph look like? I also reviewed this in class. Imagine you throwing a ball up in the air, and you define your coordinate system y as a function of time in such a way that the location y equals to 0 is the location where your ball, I had a t-ball in class, leaves your hand. Then you have an initial velocity. So initial velocity is upward, is positive, and the initial location is at y equals to 0, leaving your hand. So now out of that location you draw now the respective slope. Well, you have an upward positive velocity, so you have a slope here which is not 0 for a parabola, but upward here. And the acceleration is now min ay equals to minus g. So therefore the parabola is oriented like this here, in contrast to a parabola with a positive acceleration, which is pointing upward. Here the parabola is downward. So now therefore the maximum height that you can achieve is restricted, namely once you obtain the y component of the velocity as 0 value. And you see this reflected here. The slope here is now 0. And then from that point onward, after moving through this height here from the initial location to the maximum height, the whole aspect reverses itself, so that a t-ball then flies back down here until I catch it again. And since I catch it at exactly the same height, that velocity here, the magnitude of that velocity here and the magnitude of that velocity here reflected by that slope is exactly the same. However, in direction it is of course directed upward here, but downward here. So positive slope here, negative slope here. And you very nicely see this now in the velocity versus time graph here. The initial velocity positive here, v naught, reaching the maximum point here, and then once I catch the t-ball here back in my hand at the same height here, then you have the velocity in magnitude minus v naught. So if I would ask you how you calculate the maximum height, well, then how long does it take to reach the maximum height? Then the answer should be, well, the condition here is that the y component of the velocity equals to 0. And how would we evaluate this? Well, we would go back here now and take the y component of the velocity as v naught minus gt and set this equations equals to 0. So let's now go back to our in-class problem. A baseball is thrown from a cliff of height h by either dropping it to the bottom of the cliff with an upward initial velocity v naught or downward with an initial velocity v naught. So we first will sketch here the location as a function of time, and then calculate the time the baseball reaches the ground here. We're coming now to the second in-class problem concerning the vertical throw. All right, so let me first sketch here a motion diagram just to picture, make these three cases very clear, by which we are in the vertical direction dealing with a baseball. So in one case, case A, we have an initial velocity of 0 meters per second. Okay, so meaning we just drop that ball down to a certain height. In the second case, we intentionally throw this baseball up in the air with an initial velocity v naught upward. So that's case B. And in case C, we are throwing this baseball intentionally downward with an initial velocity less than 0, because it is downward here. And I label this as case A, B, and this is case C here. All right, so now the challenging part will be to sketch here a y versus time graph. So let's spend a little bit of time on that. So here's y as a function of t. And let's first begin with sketching here the height of that cliff here. So I chose my coordinate system such that y equals to 0 coincides where this ball is being dropped down. This indicates here the height of the cliff here. So this here is nothing else than a reflection of the height of the cliff here. So therefore in that coordinate system, this refers here to minus h here. So this is the bottom of that cliff here. Okay, so now for the first case here, the initial velocity is 0. Now I have to draw a location versus time graph. Therefore t equals to 0, the slope is 0. 0 slope here. Then in addition to that, I know I have to sketch now a parabola, but I can sketch a parabola upward or downward. In this case, the acceleration is negative because the acceleration is downward, y is taken to be upward. Therefore, it is a downward parabola. Starting from y equals to 0, initial location. Initial velocity is 0, so therefore I have here a horizontal line. And the parabola has to be oriented downward. So therefore, I sketch this parabola like this here. And I can extend this parabola now on the other side. 1, 2, 2.5, 1, 2, 2.5. So roughly here to show the full extent of that parabola. But what this is of course concerning the mathematical reflection of that, but the physical region is only here at t larger than 0. So let me now come to sketching of the, so that is the part A here. Let's now talk about part B. So in part B, I do have an initial velocity. So let me just choose here geometrically here this to be under 45 degrees, just to sketch this. So I do have an initial velocity, but it is upward here. So this parabola, this object goes up to a certain maximum height here. Let's say it is here, and then comes back down here. So symmetrically 1, 2, 3, 4, 1, 2, 3, 4, coming back down here. And here, since I'm catching it at the same height, the velocity will be in magnitude, of course, the same, but in the opposite direction. So let me therefore sketch this parabola like this here. And then coming back down here like this. So, okay, so let's continue the problem now that we have sketched the parabola here for case B. So now in case C, I'm intentionally throwing this baseball the other way around. So here the slope is then therefore exactly the opposite in the opposing direction here. Just graphically it will be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Roughly here. 1, 2, 3, 4. The maximum occurs exactly here. Same thing. And then here the slope here. Write it like this here. So therefore we can then sketch this the parabola like this here. In shape, these two parabolas in blue and red are exactly identical, but as you can see, they are shifted relative to y equals to 0. And what you can sort of infer then now from here, there are a couple of things here. Number one, the time it takes to reach the highest point here, I denote this as TR. Then the total flight time, I denote this as T total. And this time here, the flight time for the baseball when you throw it down intention with a downward velocity v0 to reach the ground, I denote this as time TF with subscript C here. And this time here, here in the case for part B is exactly that time. This is TF of C. But then we of course have to add this whole upward portion to that. All right, so this here is part B. This here is A. And this here is the curve for C here. All right. So now there's one more thing I want to sketch here, namely to reflect actually the velocity as a function of time. So this here is v of t. This is time here now. And now what do we expect from here? So now let's first start again with the with part A, where you started with 0 velocity, you go down here. Velocity varies linear in time. You have constant acceleration, but you have a negative slope here. Then, in the case of part B, where you throw this baseball up in the air, you have a positive upward velocity, but the same slope, because it's subject to the same type of acceleration g. So it would behave like this. And then in the other case, in the case C, you draw here parallel lines. Same acceleration would be like this here. So this here is part B, part A, and this here is here now part C. And these velocities here, this is the plus v0 minus v0. The initial velocity is either upward or downward, or in the case of part B, this 0 velocity. All right. Okay, so now let's now analyze this problem quantitatively. So now the first part I want to do is, so let's now first discuss case A. So where the initial velocity is 0. So let's first write down what do we know about this. Y of t equals to y naught plus v0 yt plus a half ayt squared. Here, the initial conditions are y0 equals to 0 meters, the initial velocity v0y equals to 0 meters per second, and the acceleration ay equals to minus g. So, therefore, we have for y of t a rather simple function, minus a half g t squared. Okay? And therefore, let's now evaluate how long it takes to reach the bottom of the cliff of height h. And when we analyze this in this diagram, as you can see here, let me remind you, we're not dealing with case A. Y of t, the time it takes to reach the ground, this is here. Would be the time here to reach that bottom of the cliff. Y of that time equals to minus h now. So y of tf equals to minus h. And from that point onward, this is now a simple math problem. So we would have then minus h equals to minus a half g tf squared. And therefore we can solve this for tf. tf for case A, this equals to then 2h divided by g and the square root of that. But now you see here, when I solve this for tf squared, I take the square root of that. Then you normally have plus minus. Mathematically, you see exactly these two solutions. Here's the positive solution, here's the negative solution, for which y of t equals to minus h. But of course, the only physical meaningful solution is the positive solution here. So that is now already part A. We're already done with that. So let's now continue with part C. Case C first. So now let me also write here down y of t equals to y naught plus v0 yt plus a half ayt squared. And now here we have y naught equals to 0 meters, v0y equals to minus v naught, and ay equals to minus g. Therefore, let's evaluate this now. So also here y of tf equals to minus h, same thing. But now this looks a little bit more complicated because you have now an initial velocity which is different from 0. So therefore we have now here minus v naught tf minus v naught, minus v naught minus v naught tf minus a half g tf squared. And then this is a simple quadratic equation to solve. Ax squared plus bx plus c equals to 0. x1, 2 equals to minus b plus minus the square root of b squared minus 4ac divided by 2a. So if you solve this therefore to the proper form, then you have here g tf squared. You multiply this equation by 2 and bring these two terms to the other side. Then you have here plus 2 v naught tf minus 2h equals to 0. So now we can simply take the square root of that and therefore have then the following. So TF, the two solution 1, 2 would be then the following. Minus 2 V naught plus minus, and then you have here 4 V naught squared plus, you have here minus 4 AC, so minus is plus, 4 times 2 is 8 GH. 8GH divided by what is now here 2A is then 2G here, divided by 2G. So in the only positive solution, so here you have minus 2 V naught. V naught is by itself positive. This is positive. So therefore, the only positive solution would be the one with a positive sign here. And that term by itself is larger than 2 V naught because you have here V naught squared. And therefore this is the only positive solution. So TF part C is therefore. So we can divide out now here V 2 over 2, so it is minus V naught over G. And then we have here plus the square root expression here. So we have here V naught squared divided by G squared. Because you take the 2G underneath the square root expression. And the same thing here, 4GH divided by 4G squared. So that gives us 2H over G. All right, so that is now the time for part C. And then we come now the last part for part B. This is a little bit more involved now. Okay, all right, so this is page 2 now. So now let's go back now to case B and solve that. Case B. So now what do we have here? First, let me remind you what we now have to evaluate is this time here. This in part B, the base mark goes up, reaches the highest point, comes back down, flies through the same height where it left my hand, and then it goes down to the ground. So basically this part we have already done. This is part C, but we have to calculate now this time here. So the total time equals to twice the rise time. So how do we evaluate the rise time? Well, by evaluating when the y velocity component is 0. So Vy of t equals to V0y plus AYT. So now what do we have? Initial conditions are V0y is an upward positive velocity plus V naught, AY equals to minus G, and V of t are the rise time equals to 0 meters per second. So therefore we can calculate the rise time simply to solve this for t, setting this equation to 0. This is rather simple. Then we have here simply the ratio of V naught over G. So that's the rise time. And then the total time, t total, meaning referring to this time here, this is then twice that much. So this would be then 2 TR, and that equals to 2 V naught over G. Okay. And so now let's put this all together with the result from part C, part C. So therefore we have TF for part B equals to the total time plus the flight time for part C, and then we have 2 V naught over G, and then from part C we have minus V naught over G plus that square root expression of V naught squared divided by G squared plus 2H over G. So therefore we have TF part B equals to V naught over G, 2 V naught over G minus V naught is V naught over G plus the square root term of V naught squared divided by G squared plus 2H over G. And I want you to look at the result now and think about what do we get for H equal to 0. So for H equals to 0, meaning it would not fly down here to ground, then you would only have this time here coming back here, then you have 2 V naught over G, then you simply have the total time, so only the upward part here. So now there's an alternative approach on how to solve that, to come to exactly the same result without first calculating the rise time, taking the total, the 2 times of that, and adding the result from part C. There's an alternative approach and also a consistency check. Namely, what do we know for y of t? Y of t equals to v0t minus a half gt squared. Okay? Positive velocity, negative acceleration. So now here, just like in the other two cases, y of tf equals to minus h. That function I evaluate now when this red function equals to minus h. So I should get this solution and this solution here. So therefore, what do I find? So I have here now minus h equals to v0tf minus a half g tf squared. I solve this now, putting this into the proper form, gtf squared minus 2v0 tf minus 2h equals to 0. Just bear with me for a second. And then what do we have? The solution now is therefore tf for part B, let me write out here the actual applying the quadratic equation formula. So tf, the two solutions would be therefore, here you have minus 2v0. So therefore you have 2v0 plus minus 4v0 squared plus 8gh divided by 2g. So therefore we have v0 over g, the positive solution. The negative solution would be v0 minus here, because that term is clearly larger than 2v0. So that would be plus, and then the square root expression v2 v0 squared divided by g squared plus 2h over g. Okay, so I want you now to reflect on something a little bit. this, we obtain now the solution here. This is the result here now. And this is completely identical to what we just obtained before here. Look at these two results here. This part here is completely identical to this part here. And this is this time here. Okay? We also obtain mathematically this time here. Okay? But this time I would expect now is to be identical up to a sign to the result that we obtained in part C here. Just from the symmetry of that, since I have chosen that the magnitude of the upward velocity and magnitude of the downward velocity is identical. So let's check this. So in case of part C, I have here minus V naught G plus this particular term here. So now let's have a look at this here. If I take the negative solution now in part B, the negative of that, this would be minus 2V naught over 2G, so minus V naught over G. This is exactly what you have here, minus V naught over G, plus that square root term. Now let's take the negative of that negative solution, minus if then plus. So just by symmetry, we do see that this result here, the negative solution for part B, is identical. The negative solution, the negative of the negative solution is identical to the positive solution in part C, just by symmetry of the initial conditions. Okay, so let's see. I think this is it then. So what I want you to really reflect on every time when we're doing this, we went through first part A, then part C, and then part B. And part B we solved in two ways. Let me first reflect on the part that we did for all three of them. That the function y of t has to be equals to minus h, and we solved this then. It's entirely a mathematical problem. For part A, this was very simple because the initial velocity is 0. In part C and part B, we had to solve a quadratic equation. That was the case what we just did in part B. In part B, however, we did an alternative approach, namely to calculate first the total time as twice the rise time and added that additional part from part C. And that worked simply because the initial conditions have a symmetry, namely the magnitude of the upward velocity for part B is identical to the magnitude of the downward velocity. Please reflect on that. Okay, so let's now do the last part here when we're now discussing two-dimensional motion, now that we finished this in-class problem of vertical motion. I first want to remind you of some general aspect now of motions in 3 dimensions and how do we account for this. And in fact, in one of the first classes, we in fact did that. And what I show you here is a location vector drawn in a 3-dimensional right-handed coordinate system, x, y, and z. And you see here that that vector points from the coordinate origin to that point P, characterized by coordinates x, y, and z. And the vectorial description of that vector is now shown here on the bottom, xi plus yj plus ck. So now imagine that vector describes the location of an object. And at a later time t, that object is a different location. And this is precisely what is now shown here. So initially imagine it was here at P1. At a later time it was at point P2. This is in fact exactly what I went through with you in the very beginning. So meaning that object is displaced from point P1 to P2. The average velocity is then the displacement vector over which that displacement occurs, delta t. That's the definition of velocity, displacement over time. In this case, the displacement vector in 3 dimensions over time. And now let this displacement, this time interval go to very, very small values. And you see here in the blue dashed line here, the actual trajectory. Starting from here, you consider point P1 here, and then P2 here. And now let this time interval go smaller and smaller and smaller and smaller until delta t going to 0. Then delta r is pointing in which direction? In the tangential direction locally to this particular path of this object here. And this is something what you need to understand. The displacement vector locally between two extremely small timestamps, delta t going to 0, points tangentially into the direction of the locally of a point that you're considering. So therefore the instantaneous velocity is constructed, the direction of that, as the tangent to the current location of an object on a given path here in 3 dimensions. So now let's come now to summarizing this relative in 2 dimensions. You see here y is a function of x here. You see here a particular path of this particle here. You see here at a particular point P here, now constructed a tangent line here that represents the direction of the velocity here, and now decomposed into 2 directions, namely an x component and a y component. So let's summarize this now in terms of equation. The average velocity equals to the displacement vector divided by time. To come to the instantaneous case, we let delta t go to 0, then delta r divided by delta t becomes the differential displacement vector dr divided by dt here. Keep in mind dr is a vectorial quantity here. The acceleration is then the rate of change of the velocity vector, delta v over delta t, and also in the instantaneous case, acceleration is dv dt here. So now for the concerning the acceleration and change of velocity, this is quite a little bit more tricky now. And let me slowly go through this here. Let's first have a look again here at the acceleration equation here. Namely, acceleration vector equals to the change in velocity vector times delta t. And imagine, I want you to now in your mind multiply this equation by delta t. Then the change in velocity vector is the acceleration vector times delta t. And this is precisely what I have written here. The change in velocity vector equals to acceleration times delta t. So meaning the change in the velocity vector is governed by the acceleration, just like the change in the location through the displacement vector is governed by the velocity vector here. So now imagine now an initial time t and then a later time t plus delta t. What is then the velocity? So the velocity is therefore v equals dv naught plus a vector a times delta t. That is that additional change of the velocity. So now if you read this now vectorially, it does not have to be that the vector v naught is in the same direction as the acceleration a. That's a very special case, meaning in where a and therefore the velocity v are collinear. Let me show you an example for this, and this is what we encountered so far in 1 dimension. Velocity v naught, the initial velocity, now the acceleration is in 1 dimension, increasing the velocity. So delta v is a times delta t. The final velocity is v naught plus delta v here. So a large in magnitude pointing in the same direction. Imagine a car is slowing down. Initial velocity, the acceleration is now pointing in the opposite direction, and therefore the velocity vector v here, still along in 1 dimension, has a smaller magnitude, but pointing in the same direction, v naught plus a times delta t. So that is where a and v are collinear. So now imagine a and v are perpendicular. So therefore, let's begin here at a velocity vector v here, and the change of the velocity is accounted for by a very specific direction, namely for which the acceleration is perpendicular to the initial velocity. then you can construct at a later time delta t a new velocity vector. And then you continue like this here, and imagine this acceleration in magnitude is a constant and is always directed perpendicular to the velocity v here. So what kind of path does now this velocity vector describe here? It's like in a circle here. If you take both cases together, in general, namely initial velocity v here, and not where the acceleration is only collinear or only perpendicular, this would be a so-called general case here. And you have the general vectorial equation, vector v here equals to v naught plus delta v, meaning this is the diagonal in a parallelogram constructed by velocity vector v naught and delta v here. So what I want you to take away from that is, in the case of where the acceleration is in the same direction as v naught, either opposite direction or 180 degrees, so increasing or decreasing, this is the situation we encountered when we're dealing with one-dimensional motion. When the acceleration vector is now perpendicular to that, we're coming actually then to the case of uniform circular motion. But I will discuss this in the next lecture in more detail on Thursday. So I want to now restrict myself to a motion in 2 dimensions and account for a motion where in general I only have constant acceleration. And imagine I have a constant acceleration ax in the x direction and a constant acceleration in the y direction. Then the way the velocity and location behaves as a function of time is completely defined, meaning time and velocity varies linear in time and location varies quadratic in time. We will now consider a special case of that, namely where we're throwing a stone off of a cliff, giving it an initial horizontal velocity. There is no further acceleration. Let's ignore air resistance or anything like that. So meaning ax is 0. However, that stone will be subject to gravitational attraction. So the constant acceleration here is minus g, whereas in the x direction it is 0. And everything then follows from that. And I will calculate this problem now in more detail. Here is a link to a demonstration. Namely, if you drop an object, a little metal ball, just straight down, compared to if you give that little ball initially an initial horizontal velocity, to compare the time it takes for these 2 metal balls from the same height relative to ground reach the ground at the same time. And it turns out this time is exactly identical. However, in horizontally, they reach the ground in different locations. It's just because in one case where you give this ball an initial horizontal velocity, it's just displaced. Whereas in the other case where you drop it straight down, this part is 0. However, they are flying exactly through the same height here. And you see here, there's no x component appearing in here. Imagine you'd place your coordinate system at the initial location at 0, so this term would be 0. You're not giving it an initial velocity in the y direction, so this term would be 0, and all what you have left here is then minus a half gt squared, and that equals to minus h if you draw your y-axis upward. And this would be in both situations exactly the same thing. I encourage you in the posted PDF file afterwards to click on this link. There are a couple of 2 questions to this and watch this carefully where you see this exactly demonstrated. So the part which I want to now calculate, and this is the last part for this lecture now, is exactly this horizontal throw. So in the x direction, the initial conditions is an initial velocity in the x direction. And this is shown here by a ball, which a little metal ball then give you an initial velocity in the x direction. In the y direction, you have no initial velocity in the y direction. That's what I want to calculate. So this would be simply minus gt. So this ball would be now dropping in the y direction subject to the gravitational attraction. And the y component of the velocity would be simply increasing linear in time, and this initial value is 0 here. And this is completely identical to a case where you have a metal ball here and you simply drop it straight down. And here is a problem with some numbers here. Namely, here you have the motorcycle here, movie stunt driver. Here's the y-axis upward, x to the right here. So this is the initial location. This is x, y equals to 0. Acceleration is g, downward here. So the component of the acceleration, the y component, is therefore minus g. The height of that cliff is 50 meters, and where it reaches the ground is 90 meters off of the cliff here. So in that coordinate system, y equals to minus 50 meters. And then there's a question here, how fast must the motorcycle leave the cliff top to land at ground below at 90 meters? From the base of the cliff where the cameras are, ignore air resistance. So this gives you a little application to this problem, and I will solve this problem now in somewhat more general terms. Okay, so that concludes then this class for week 3 on day 1, but I will finish now the explicit calculation of the horizontal throw. Okay, so let's do the in-class problem of the horizontal throw now. I will leave the numbers up to you using this concrete example. Horizontal throw. So beginning is first to draw various graphs right now. So x, y is a function of time. We will do this in a second. But let me in fact first sketch here, and I will prove this to you, the actual trajectory. And let me make here a very, very clear distinction. I mentioned this in class already here. I'm drawing here the actual shape of the path. This is not the time dependence. That's not the same thing. So I'm throwing literally, let's say I'm standing here at the height of a cliff, height h, right here, and I'm throwing a stone in the horizontal direction. Then you would expect this stone to eventually reach the ground here. The question is, what type of shape does this trajectory have? And I will show you today that the shape of this trajectory is also a parabola. And it is entirely a consequence of the following. When you're throwing the stone in the x direction, it has no acceleration in the x direction. It has an initial velocity. So how does the location and therefore in x vary in time? It varies linear in time because you have no acceleration. However, in the y direction, y, and imagine I'm not giving it an initial velocity in the y direction, only in the x direction, so the y component of the velocity is 0. It simply drops down here, just like this little video, what I want you to watch, a metal ball dropping it straight down or giving it an initial velocity in the x direction. But that location y as a function of time varies quadratic in time. And since here the initial location is 0, the initial velocity in y is 0, so you have something very simple. Minus h equals to minus a half gt squared. So location varies quadratic in time. Location x varies linear in time. If you now solve time for x and insert this back into y of t, you can already see in your mind that y of x will be a parabola, where it's quadratic in x squared, in fact. And I will show you this explicitly. All right, so let me now sketch here side by side here the velocity in x and the velocity in y here first. So t, this is v y of t, and this is v x of t. So concerning vx of t, you have an initial velocity at t equals to 0 and remains constant like that. Whereas in the y direction, you have 0 initial velocity and the velocity increases linear in time subject to the constant downward acceleration. So let's say it would be like this here, reaching the ground then at that time here, tf here. So that concerns now the velocity and the y component as a function of time. So let me now sketch here side by side y of t and x of t. So what do we expect for this here now? So let's first look at y of t. Y as a function of time, and here x as a function of time. So this is t, this here is x of t, and this here would be y of t. At y equals to 0, what type of, this is now y as a function of time. The rate of change of location in time is a measure of the velocity. There is no velocity here. So there's 0 slope here. So therefore you sketch here your parabola downward here, negative acceleration, until you reach the ground here of this cliff at minus h. That would be the graph for y of t. For x of t, on the other hand, you have no acceleration, you have constant velocity therefore. So the velocity, the x location linear increases in time here. So here you have a slope, not like here where there's 0 slope, because here v0x is different from 0. In contrast to here, v0y equals to 0. Okay, so you see here I have not written down a single equation here. I've only reflected on the general behavior of these two more independent motions in the x and the y direction. In x direction, no acceleration, time varies linear in time, constant velocity. In the y direction, no initial velocity. We expect a parabola downward, negative acceleration, velocity increases out of 0, linear in time. If you combine this now, y versus quadratic in time, x versus linear in time, you solve for time, insert this back into here, you come then to mathematically the shape of a parabola, and I show you this explicitly here. But this is the trajectory. Y is a function of x. Do not confuse this with y is a function of time, even though you have also here mathematically a parabola. I will come back to the aspect, what does this slope on y as a function of x tell us a little bit later. The slope on a y or location as a time graph is nothing else than the velocity. And for a location versus location graph, namely the trajectory y is a function of x, the slope tells us something different. But I come back to that a little bit later. It's namely related to the ratios of velocities in the x and y direction, but we'll come back to that a little bit later. So now let me solve this quantitatively, basic equations right now. So in the x direction, in the y direction, so what do we have? So in the x direction we have ax equals to 0. We have v0x, the initial condition is velocity different from 0. For the y direction we have ay equals to minus g. Therefore we have vx of t equals to v0x, and this is simply a constant. And the location x of t is therefore x naught plus v0x times t. But since I've chosen the coordinate system such that the initial location coincides with the coordinate origin, so therefore x of t equals to v0x times t. Something rather simple. So that concerns now the x direction, the complete quantitative description of the x direction. In y, we have vy of t equals to v0y minus gt in general, but here there's no velocity, initial velocity in y. So therefore we have vy of t, something simple, minus gt. And y of t is in general therefore y naught minus a half gt squared, since I already took into account that the initial velocity in y is 0, but now the initial location is also 0 here. Here y naught equals to 0. So therefore I have y of t equals to minus a half gt squared. So this is something rather simple here. So now we can evaluate the flight time. Namely the time it takes to reach the ground. So this is y of tf equals to minus h, exactly the same thing what we did when we discussed the vertical throw. So insert this back into here, then we have h equals to a half g tf squared, or tf equals to 2h divided by g and the square root of that. And the flight distance is therefore flight distance in x is therefore, we take that time here, insert it back into here. So therefore we have here xf equals to v0x times 2h over g and the square root of that. So let me just highlight the main findings here now. The flight time and the horizontal distance from the base. So, and now there's one more thing to do. You can, we can, in fact, formulate the height here, solve this in terms of xf and v0x. So this would be then h equals to, so you solve this for h here, this would be therefore xf over v0x squared times g over 2. So it would be half g times xf over v0x squared. And you see this immediately. This is in fact coming directly from here, minus h equals to minus half gt squared, but the time is 2h over is taken from here as x over v0x. So please go through these derivations carefully yourself. If you just watch this, you have heard me saying this several times before, this is pretty useless. So now the last part to demonstrate to you that we indeed get a parabola is the trajectory. And this is now really simple to show. So you have here y of x equals to minus a half g t squared, but now I replace g by what? By x divided by v0x. So then we have here x divided by v0x squared, and then let me just highlight the main finding here right now, minus g, and let me take the constants out, 2 v0x squared times x squared. So there you see your parabola behavior for the trajectory. Okay, so please go through, so the parabola here and the sketch what I've shown you here were inferred that I do expect it's a parabola, but here's the explicit relation, and it comes directly from the fact that y varies quadratic in time here, x varies linear in time here. You solve for t, and then you get here x v0x squared. So t squared goes into x squared due to the very fact that in the x direction there is no acceleration and x is proportional to the time here. Okay, so that concludes now week 3, day 1. Please do not just stop here after you maybe watch this video. Go back and watch it again and take notes. I'm expecting you that you follow the derivations of the 3 main problems what we did in class. The motorcycle in the car, number 1. The vertical throw, the 3 cases A, B, and C. And now the horizontal throw. You need to be able to with a clean sheet of paper, solve these problems yourself. And if you're stuck with something, come to office hours or send me an email, or find me in class afterwards next week once I'm back. Thank you.